Lesson 3.8 talks about how to graph all rational functions, whether they are proper or not. And of course, we already know that we can use the numerator to find the zeros of the graph, and we can use the denominator to find the asymptotes. We're going to simplify this by making just 3 simple steps to find any graph of any rational function. First of all, make everything into linear factors. Well, the numerator here is already done. It's already x minus 2. That's a linear factor. The denominator, though, we can factor into 2 linear factors. It's a quadratic, so we can factor what multiplies to equal 6 and adds to equal negative 5, of course, is x minus 3 and x minus 2. From there, always reduce if possible, and that means to just cancel out anything that you can. You'll notice that the factor x minus 2 is in both the numerator and denominator, which means that we can cancel. Now, what we've got to remember is that x minus 2 did exist in the denominator, because you may remember that the denominator can never equal 0. And even though we've canceled it out, it was still a part of the original function. But ultimately, what we're left with is 1 over x minus 3. Now, hopefully you remember how to graph this. It's a fairly simple graph. X minus 3, we're now on the 3rd step. We're finding the zeros and the asymptotes. There are no zeros because the numerator has no zeros, but the denominator has a 0, and that will become our asymptote. And that, of course, is x equals 3 is a vertical asymptote. Now, if we were just going to graph this like normal, which we are, we remember this is a positive function, positive, positive, look at those dominant terms, and remember that it needs to be constrained in this area. Once again, we're just sort of using some logic, and we're going to be able to graph it this way. When it jumps over the asymptote, it's going to go like this. So that's what this graph roughly looks like. However, remember that we canceled out those x minus 2's. So 2 cannot be a part of the denominator. Now, it's not a 0 like it would be if it were in the numerator, and it's not an asymptote like it would be if it were in the denominator. It just can't exist because it did exist in both. It cannot be there. So what we're going to do is we're going to come over here, and where x equals 2, we're going to change that to a hole in the graph. And so we're going to graph it just like normal, but just leaving that little bit of a hole there. So let's look at this one that's already been factored out, and we're going to find the zeros, the asymptotes, and the holes in this graph. Now, it's already been factored into the linear factors, so we should be able to figure it out very easily. Now, the key is to, first of all, I like to find the holes in the graph first because they're actually the easiest. They're the ones that exist in both the numerator and denominator. Do you see any factors that exist in both? Well, you should, that x minus 3 will cancel out. So that means that the factor x minus 3 has to do with the holes in the graph. So therefore, there will be a hole where x equals 3. Now, hopefully you remember that zeros are always the zeros of the numerator. Those are the x-intercepts. And you can see there are 2 factors that are involved there. X plus 2, which means that x equals negative 2 will be a 0. And then x minus 1 is a factor, so x equals positive 1 will be a 0. Hopefully you can also tell now the asymptotes are in the denominator, and there are 2 factors there, so where x equals negative 5 and x equals positive 7, there will be a vertical asymptote. Now, with just that much information and knowing that this is a positive graph because all of these x's are positive, you should be able to graph this whole thing. And it would look kind of like this. We're not going to go into all of that right now, but hopefully you could figure it out knowing that this section on the right had to start up here. You flip every time you hit an asymptote, leave a hole where it says there's going to be a hole. Obviously it's going to cross at everywhere there's a 0, and then you're going to flip every time you've got an asymptote. We're going to talk a little bit more about that on the next screen. Now, we've talked quite a bit about vertical asymptotes, and vertical asymptotes, as you remember, are where the denominator would equal 0. So down here in the denominator, we'd set that equal to 0, and that would be our vertical asymptotes. However, occasionally we get horizontal asymptotes, and horizontal asymptotes usually happen when we have proper rational functions. That's where we have the numerator with being a smaller degree than the denominator. When you have a horizontal asymptote at the x-axis, in this case, when you have a proper rational function, the x-axis is a horizontal asymptote, and we've talked about that a lot. We've seen things like this happen, horizontal asymptotes at 0. However, there are some cases where you can get horizontal asymptotes on different places. This usually only occurs when you get cases like this, where you have the same degree in the numerator and denominator. When you get the same degree in the numerator and denominator, sometimes your horizontal asymptote will be at a different point than the x-axis. And here's the easy way to find it. The simplest way to find it is just to simply look at the ratio of the coefficients. So in this case, the horizontal asymptote will be at 3. So if you were to graph it out, you would realize there would be a horizontal asymptote at that point, at 3. Notice this particular function. Also, it has the possibility of having a horizontal asymptote because it is the same degree in the numerator and denominator, both x to the 4th. So you need to look at their coefficients and just write out that fraction, 3 over 18. Of course, that can be reduced and change into 1 over 6. But what that means is that 1/6 is the horizontal asymptote. So if you were to graph it, obviously 1, 2 would be there. 1/6 would be just barely above the 0 line. But that would then be a horizontal asymptote of this function. So if we're going to try to graph a very difficult rational function like this one, we need to just put everything together that we've already learned. Remember what we've learned about the numerator, the denominator, the asymptotes, the zeros, everything about it. We're just going to put it all together. First thing I would like to do is I like to always try to find the y-intercept first. Remember, the y-intercept is when you just punch in 0 in for all of the x values. Of course, that means this first term will come out to 0, the second term will come out to 0, and the numerator will be left with -4. The denominator, of course, will be left with -3, which tells us that the constant in all of this, despite the fact that it's a rational function, the constant is simply -4 over -3, or in this case, the y-intercept ends up coming out to +4 over +3. Once again, those negatives cancel out. Now that is going to matter because that will be where it intercepts the y-axis, 4 over 3. The next thing I like to do is I always like to go ahead and find my asymptotes next. So we look at that denominator and we find out where does the denominator equal 0. So let's drop down here and let's do a little bit of math. X squared equals 3. We can take the square root of both sides and get x equals plus or minus the square root of 3. Those will be our asymptotes. Now, if you are keeping score and just trying to think about how to graph this, let's go ahead and just make a very simple graph right now. We already know a few things. We already know that the y-intercept is at 4 over 3, which is just right around in there, 1 1/3. We've already found our asymptotes to be at the square root of 3. The square root of 3 is a little bit less than 2, and so we're going to go ahead and graph our asymptotes somewhere right in there. So we have two asymptotes and we have a y-intercept. Now from here you might think it would be valuable to go ahead and find the zeros, and it would be, except there's one small problem with this particular function. If you try to find the zeros of this one, you will realize there are no rational zeros. Now, there will be at least one real zero. You may recall that anytime you have an odd function, that those imaginary or complex zeros have to come in pairs, leaving us with at least one real zero. So there will be a real zero, it just will not be rational, which means we won't be able to find it using the rational roots theorem and synthetic division like we're used to. Now, you may think that's a complete failure and there's no way we're going to be able to do this problem, but let's just remember that it has at least one real zero, but it's not rational. And so we'll come back to that, and I'm going to show you how to graph this without even knowing what the zero is. We'll just be able to figure it out on our own as we go through this. Okay, so here's the one last thing that we haven't learned yet, and that is what's called an oblique asymptote. Now, a graph has an oblique asymptote only under certain conditions. The first condition is that the numerator must be exactly 1 degree higher than the denominator. So we have that particular scenario, but that's the key. An oblique asymptote only exists when the numerator is exactly 1 degree higher than the denominator. And it also exists that if you went ahead and divided this out, you end up with a remainder. So oblique asymptotes only happen under these very special circumstances, when the numerator is 1 degree higher than the denominator, and there is a remainder when you actually divide. So we have the first one, we've got that. Let's see if we get the second. Let's go ahead and divide this out. Now, you may not remember how to do long division, so that's why I'm here to help. It's been a while since we've worked long division the long way, not by using synthetic division. Now, we have to do the long way here because this is not a linear factor, it's x squared. So we've got to make sure we do this. We've also got to make sure we put in a 0x there as a placeholder, and we're going to divide this out. So let's go ahead and do this. 2x cubed divided by x squared is 2x. We multiply that out, we get 2x cubed, and then we go ahead and multiply it by the 3, so we get minus 6x. Well, that doesn't work there, so what we're going to do is we're going to slide it over. You may notice that the reason is it doesn't match up with this 6x, so we're sliding it over to the 0x spot. So now we can go ahead and subtract all of this. Of course, that comes out to 0. This just comes straight down, 0x squared, and now 0x minus negative 6x comes out to plus 6x. We can divide again. X squared, negative x squared divided by x squared comes out to negative 1. Multiply it down, you get negative x squared, and then 3. Of course, we're going to put the 3 over here so that we can do the subtraction. That comes out to 0 like it should. 6x just comes out to 6x, and then negative 4 minus 3 comes out to negative 7. Notice we can't divide this anymore because we have 6x and we're trying to divide by x squared, so this is our remainder. Once again, all that does is just checks off, yes, there is a remainder when you divide. You say, well, that's just a lot of work just to see if there's a remainder. Well, the good news is this wasn't just a lot of wasted work, because here's the key. This right here, 2x minus 1, is our oblique asymptote. 2x minus 1, that is a linear function, and it is our oblique asymptote. So I hope you remember how to graph a line. 2x minus 1 is our oblique asymptote. That means that negative 1 is the y-intercept of this asymptote, and it's got a slope of 2, so it's going to go like this. Once again, it doesn't have to be drawn perfectly, but it does have to be drawn as carefully as possible. So we have an oblique asymptote. That means it's a line that is not horizontal, it is not vertical, but this new graph will not cross it. So it may look confusing at this point, but we have a positive graph, so that means it's going to be up and to the right. So when we start on the far right, it's going to be up, but notice we have two asymptotes. So it has to be in this general area. Once again, just use some logic and some common sense, and you can realize it has to look like this. Now, once again, I know usually we just work right to left, just jump over the asymptotes, but because we have an oblique asymptote, this is a unique situation where we're going to start at both ends. So if this one is over here, the other one has to be between these two areas, within that oblique asymptote and the vertical asymptote as well. And once again, using some common sense, we realize it has to look like that, getting closer to the oblique asymptote and the vertical asymptote. And now, as we jump over the vertical asymptotes going both directions, we'll realize that we have to have a 0 somewhere in the middle there. Remember we talked about that earlier? We have to have a 0. Here's what's going to happen. It's going to jump to the bottom on the right side, and it has to cross somewhere and still end up at that y-intercept. And then it's going up here. The key is it has to hit that y-intercept, and it has to be on the opposite sides. I don't expect this type of problem to be super easy most of the time, but let's remember just a couple of things. First of all, remember that the vertical asymptotes always come from the denominator. Remember that the y-intercept is always found from the constants at the end of the function. And then thirdly, you will have an oblique asymptote when there is the numerator has 1 degree higher than the denominator, this one does, and when there's a remainder when divided. That's not a wasted exercise to divide because your answer is your oblique asymptote, and in this case, it came out to this nice slanted line here of 2x minus 1. When you finally go to graph, start where your oblique asymptotes will come into play. And they will come into play on the 2 far ends. And that's it. Notice here it even crossed the oblique asymptote right in the middle. That's okay. It's allowed to do that. It only comes into play at the very ends of the graph. And from there, you can just jump over the asymptotes, the vertical asymptotes, and graph from there.